Alright girls, so just to finish up this PowerPoint, this will be really short, maybe 5 minutes, but I wanted to put them in little easy chunks for you guys to digest and work on your own time in the next couple of hours that we have together. So DNA replication is going to start at these locations called the origins of replication. And they're just little spots all the way along the DNA double helix that will open up and allow DNA replication to begin. They're just called origins of replication. When they do open up, when that DNA unwinds at the origin, we call that the replication bubble. And along the DNA sequence, there are tons and tons and tons of origins of replication, and there are tons and tons and tons of replication bubbles all working at the same time. So replication is going to basically move forward in both directions on either side of the bubble. So if you flip to the next slides, you'll see here that you have our bubbles, right? And so they'll open up here at the origins, and then DNA helicase will unwind in either direction. So it's going to go both ways there, okay? And then what you're seeing here in this slide is the whole process basically over time. So this is the beginning, and this down here is our end product. So in the end, we get our two daughter strands that we just finished replicating. So from step 1 up here, you see a bunch of openings. Step 2, you see that DNA replication is basically just continuing, which is why the bubbles are getting wider. And then eventually the bubbles end up running into the bubbles next to them, which ends up flattening out to this third picture that you see. So basically the replication bubbles just run into each other, and when they do, then all of the enzymes that we talked about in the last couple of videos, they all just kind of fall off and wait until it's time for DNA to replicate again. So going back up here, replication ends, see, when the products from the bubbles merge together. So that's what I was just explaining in that last picture. And then remember, DNA replication always occurs in the 5' to 3'. It will never occur in any other direction. If it does, we haven't found it yet. It's always going to move in the 5' to 3' direction. And then replication is continuous on the 3' to 5' template. So if helicase is moving from the 3' to 5' on the old strand, then you know that what's being built is the anti-parallel 5 to 3. And we know, since we add from the 5 to 3 direction, like we said up here, then we know that this is our leading strand. It's continuous. And then if we flip to that last picture, if we look at our 3' and our 5' end, we can see that this is our 5 to 3 that's being built, right? 5 to 3 is being built. So we know that that's our leading strand. And then if we look back at the slide that we were on, replication is discontinuous on the 5' to 3' template. That's because when we are building, the helicase is going that way, but we have to replicate in the 5' to 3', which is going the opposite way. And so again, if we look at our picture, here's our helicase, in this case, is moving from 5 to 3, and so replication has to move in the opposite direction. So that's why we get all these little Okazaki fragments that have to be built. because the replication is discontinuous. That is our lagging strand. Okay. So if you have any questions about that, please feel free to Skype me about it. I will probably be on the couch in my PJs with my puppy dogs. So, yeah. So the proteins, we've talked about them. So DNA polymerase. If you remember, I don't know why I did that. If you remember, I said a couple times that DNA polymerase can add 50 new nucleotides per second. If we only had one origin of replication instead of all those individual bubbles, then if that were the case, then it would take 2 years at this rate. Literally 2 years for all of your DNA to be replicated. But because we have several origins of replication, we have several bubbles, and we have hundreds of thousands of DNA polymerases all functioning at the same time, it actually takes more like 12 hours instead of 2 years. So that's really good for us, because if you remember the whole skin situation, when I'm walking around brushing my skin off in class, if it took 2 years, that would be no bueno for any of us. And then DNA ligase. Remember, ligase is the one that hooks our Okazaki fragments together on the lagging strand. Talked about this. So the last thing I kind of just wanted to add, I'm not gonna like put this, well, I don't think I'd put this on the assessment. I probably won't, but then again, I'm still trying to figure out how I want to do the assessments, because I still want to get you guys some quiz and test grades in, but I don't know how to do it in such a way that I know that you will also pass the honesty test. So I'm debating doing open book, but haven't decided yet. We will see. I will continue to brainstorm. But anyway, if we look on here, we're looking at a DNA segment. And we keep saying that DNA polymerase can only add to the 3' end. It can only add to the 3' end, and we've said that over and over and over and over and over again until we're blue in the face because we're out of breath from saying it so much, not because we have the coronavirus. The 3' end is the only one that has this available hydroxyl group. If you remember that functional group from biochem, that hydroxyl group. Okay. Hydroxyl group. Okay. That hydroxyl group is why we are able to only add to the 3' end. Because if you look at the 5' ends, there's only phosphate groups. There's no free hydroxyl groups available. And if you remember, this would be one of those cases where I would ask you guys a question and then I would stare at you all blankly until you answer me. Don't have that luxury through here, so I'll kind of just go for it this way. But if you remember, when we are building macromolecules, when we were putting things together, what type of reaction does that? We said that the type of reaction is called dehydration synthesis. Right? Some of you are currently having flashbacks to biochem. Okay, but this dehydration synthesis is the removal of a water molecule to put two things together, right? Well, one of the H's is going to come from here. The O is obviously going to come from here, and then the other hydrogen will come from the nucleotide that we're about to add on to this growing strand. So that is the reason why we can only add to the 3' end, because the 3' end is the only end, gosh dog it, is the only end that has the available hydroxyl group to do a dehydration synthesis reaction in the first place. Don't really think I need to say anything here. That's pretty much just the same picture as this, just in, I guess, prettier format. But let me know if you guys have any questions about any of this. And yeah, we'll move from there.